Hello everyone, welcome to our fifth experiment of PSCAD. In this fifth experiment, we will be doing modeling of inverter control scheme in PSCAD. So in this experiment, what we will be doing, we'll be modeling a PV plant having a rating of 4 megawatt, such that it feeds rated active power to the grid because we want to utilize our PV fully. So we want all the power that is generated by PV is utilized. So we want all the rated active power to be fed to the grid. So for that, let's say this is a system and we have a step-up transformer which is connecting our PV system to the grid along with a filter. Okay. So using this primary voltage of the step-up transformer, we can calculate our minimum DC bus voltage that is to be maintained at the PV side, and also the value of reference currents in DQ reference frame. Like we are here controlling the rated active power to be fed by the PV using current controller in DQ reference frame. So here uh, the DQ reference currents can be calculated using the rated power and the voltage level that we will be using. So since I want my PV to deliver rated active power to the grid, so I need a reference ID and the reference IQ should be 0 because I want to deliver active power only. So the rated power here is 4 megawatt and that I have considered, and VM is the maximum per phase voltage of the primary side of step-up transformer, and the filter inductances and capacitances values I have already provided. This is a LCL filter. You can directly use these values to design. And then for generating gate pulses to excite the switches of the inverter, I am using sine triangle PWM method. So in this controller in DQ domain, I am using a current controller in DQ frame. You can see that I am comparing the ID reference with actual ID to generate a control signal or error signal that is passed through PI controller. Okay, and then and then the modeling is done considering the dynamics of the inverter. So that we will be getting modulation indices in DQ reference frame. Then that modulation index in DQ reference frame is converted into modulation index in ABC reference frame, which will be compared with a carrier signal to generate gate pulses. So we will be plotting the instantaneous phase currents before and after the filter, and the reference currents in DQ frame with the actual currents. Then we'll be plotting the modulation index, then the gate pulses. So let's go to the PSCAD model and see. So this is the inverter. This is a three-legged inverter that I've designed using 6 switches. Then this is the filter, LCL filter that is used. Then this is the DC link voltage. Here the DC link voltage is maintained as a stiff DC link voltage. And then a step-up transformer is used to connect the inverter-based source along with filter to the grid. The grid here is modeled as a voltage source. So what it is done here is the current that is available after the filter is converted into uh, variable converted into, like, the current is present in FBC reference frame that is converted into quantity in DQ reference frame. I have separated the all phases of current. Then I have used the voltage at the primary side of the transformer as reference so that it will be given to phase locked loop. Phase locked loop generates the reference angle. The reference angle is needed to convert the quantities from ABC reference frame to DQ reference frame, because the DQ reference frame always have variables as DC variables. So we need the reference angle so that it can coincide the variables at ABC reference frame with the DQ reference frame. So what we have done is I have used this variable, this voltage as a reference to provide it to PLL. And the parameters inside the PLL can be set as this, like the proportional gain, integral gain, and the base frequency. Since my system is 60 hertz system, so the base frequency and the offset angle, everything is set accordingly. Then this PLL is provided inside this block ABC to DQ. You can see the transformation angle is given. This is the reference angle. So here I am converting the ABC quantities to DQ quantities, and the DQ sequence is Q axis lagging. This is how the model is set. So I am obtaining voltages in DQ reference frame and currents in DQ reference frame. Okay. Then after obtaining voltages and currents in DQ reference frame, I am going to the current controller so that I can compare them and compare them with the reference currents that I have calculated using the formula given in the manual. Like we can go to the manual and see the formula. And based on rated active power, I have calculated the D axis reference current and Q axis reference current. So here I have just made, I have just given the reference current here, and I'm comparing it with the actual one. So it is passed, and the error signal is passed through PI controller. The gain of the PI controllers are given here, and the dynamics of the inverter are included, so that I'll be obtaining a modulation indices in DQ reference frame. So here the current that is obtained from the after transformation into DQ quantities, that current is limited up to a certain value, because our inverter is basically made up of switches, and switches have their own ratings. I don't want my current to go beyond switches ratings, otherwise the switches will be damaged. So in this, by using this rectangular to polar transformation, I am limiting my magnitude up to a certain limit, and then I am getting the current, and that current is being compared with the reference one. So after the modulation indices in DQ domain is generated, what I am doing is I am multiplying a gain factor of as VDC by 2. There is a gain factor actually here, 2 by VDC. So that I am multiplying over here, the magnitude. So that again is converted into ABC reference frame, as I have already explained that the modulation indices in DQ reference frame will be converted to modulation indices in in ABC reference frame. And then the quantities in the ABC reference frame, the modulation indices should have a maximum value of 1. So I have used a saturation block so that the maximum value will be 1. So this is the way, and here also the angle PLL is used. You can see in the ABC to DQ, DQ to ABC. It's basically DQ to ABC transformation block. So it uses the reference angle as PLL or the transformation angle. Then after obtaining the modulation indices A, B, and C, we can see over here. We can compare with the triangular carriers. So here I've used a triangular carrier of 10 kilohertz. Then I've given the input as A, B, and C and compared with the triangular carrier to generate gate pulses. These gate pulses are for the 3 legs. And in one leg, there are 2 switches. If I'm generating the gate pulse for, let's say, the upper switch of the leg 1, then the lower switch, the gate pulse for the lower switch should be complementary to what is going to the switch 1. Leg 1. So that complementary signal is generated by using a NOT gate here. So in this way, I am providing the gate signals to my inverter switches. So this is the way in which I am controlling my current. So here the reference current you can see is 0.785 kilo amperes. Everything is in kilo ampere here. So I will be obtaining my maximum value of instantaneous current that will so should be around 785 amperes. So let's run the simulation and see. Okay, yes. it's running. You can see that this is the grid voltage, that is the voltage present at the primary side of the transformer, and this is the current that is generated by the inverter based source, and this is the modulation index that I have plotted, A, B, and C. So we can see that here modulation index do not go beyond 1, and we can see a perfect sinusoidal waves because modulation index is a sinusoidal quantity, so that it will get compared with carrier to generate gate pulses. So these are perfectly sinusoidal waves, and the current we can also see. Maybe I can zoom in. So we can see that the current, the maximum is value is around 785 amperes. So you can see the current is also perfectly sinusoidal, and it is correctly tracking the reference current that I am providing. So this current is a proof that I am obtaining rated active power from my inverter based source to the grid. So that's all about this experiment. So thank you so much.